Hello, this is Jack Jackson. We're going to start part 2 of our investigation of limits. And previously, in the last few videos, we've looked at limits informally. And in this video, we're going to start looking formally at limits and continuity. So let's start by looking at the informal definition of a limit, and remember what that was. We say that a function f approaches the limit L as x approaches a constant c, and we write it this way: the limit as x approaches c of f of x, or probably the limit of f of x as x approaches c, equals L, if and only if, when we let the input values of x get closer and closer to c without actually being c, then the output values of f of x get closer and closer to the limit L. So what's wrong with just using that as the formal definition? Well, the problem is this expression closer and closer to. That's not really precise, okay? And so that's going to be insufficient for rigorous proofs. Now, this type of terminology is what was, or something similar to this, was what was introduced by Leibniz and Newton when they invented calculus or discovered calculus. And they used this, mathematicians used this for a century, and they showed that the idea of limits and the idea of derivatives and integrals that we'll talk about later were very useful. But there was this problem with the foundations of the subject, and this persisted until about the 19th century, when more rigorous definitions and proofs of the foundations of calculus were developed. So we're going to try to make precise what we mean by closer and closer to. Basically what we want to say is this: we want x, if x is close to c, a certain distance from c, we'll call that distance delta, then f of x is a certain distance close to L. That certain distance we'll call epsilon. So we're going to make use of these two Greek letters, epsilon and delta. Now epsilon, these are lowercase epsilon and delta, and these are Greek letters. So from the Greek alphabet, of course the alphabet we use is the Roman alphabet, and the epsilon is like a Greek version of our Roman letter E, and should be interpreted to stand for the error tolerance. So it's some tolerance that you're willing to accept for an error, and we'll make this a little bit more precise in a few minutes. So think of E or epsilon for error. And D, or delta, is like a Greek version of the letter D, and should be interpreted as a deviation from the C. Now, before we even go any further, let's kind of take this idea here. So when we look at these definitions below, we're going to think of these as like defending a challenge. So the defender is going to say, okay, I believe this function has a particular limit L. So when we make this claim here that the limit as x approaches c of f of x is L, we're making a claim of this limit L for this particular function for this particular value c. But we're making a particular claim for L. Now suppose there's a challenger, and the challenger says, I think you are incorrect. You're off. And how about, I think you're off by at least some amount, and they give you a number, and that number is epsilon. Now what the defender then has to do is take the value of epsilon that the challenger gives and says, no, you're wrong. Notice that if I select this value of delta, and they pick a particular number, which is going to be based on that value of epsilon, then all of the x values within delta of c, except maybe for x equals c itself, have corresponding outputs which are within your value of epsilon of the limit. So there's no way I'm off by epsilon. Now what could the challenger then do? The challenger could then say, oh, well, wait a minute, I wanted a smaller value of epsilon. So for example, the first time the challenger may say, hey, I think you're off by 0.1. And basically the defender then says, oh, if I get close enough, make my delta small enough, and get only x's that are that close within delta of c, then the outputs, the corresponding y's or f of x's, they are within your epsilon, your 0.1 of L. And then the defender, the challenger says, well, no, wait a minute, I want a smaller value of E, of epsilon. So they pick even a smaller value. Maybe they go to 0.01. Well, then all the challenger, the defender has to do, if the limit's really right, is they just have to pick an even smaller value of delta. Now, if the defender can always find an appropriate value of delta, no matter how small a value the challenger selects for epsilon, then the defender has proved his claim, and the limit L is the true limit. Now, there's several different kinds of limits. We've already looked at them informally. We've got full limits as x approaches a constant. We've got limits as x approaches a constant only from the left or only from the right. We have limits as x goes to infinity. We have limits as x goes to minus infinity, and so forth. So let's look at a couple of these. We're going to start with the most basic one, where we started before. So the limit of a function as x approaches a constant. So we would write it like this. The limit of f of x as x approaches a c equals L. Okay, so what do we have? We have real numbers c and L and a function f. Okay, real valued function f. And we say this is true if and only if for every real number epsilon greater than 0, there exists a real number delta greater than 0, such that if c minus delta is less than x, which is in turn less than c plus delta, but x is not c, then L minus epsilon is less than f of x, which is less than L plus epsilon. You can leave out the two things in the parentheses. Or you might rephrase it a different way. Some people would rather phrase it this way. Instead of rephrasing this compound inequality as x is between here, we could do this by saying x is in this interval. So you could say x is in the interval c minus delta to c plus delta, but x is not c. And if we said it that way, we would probably then say f of x is in this interval L minus epsilon to L plus epsilon. So you could use those two instead of, so you can use this expression and this one here instead of this one and this one, and it means exactly the same thing. Or another way to say it is this. We can do it with absolute value. Remember, the absolute value of x minus c is the distance x is from c. So we say the absolute value of x minus c is between 0 and delta. This way, if I don't put the equal to here on the 0, this does eliminate the fact that x equals c. So in this version, I do not have to write the x not equal to c. And down here, we would say the distance from f of x to L, which is f of x minus L and then absolute value, is less than epsilon. Notice I don't put the greater than 0 here because the f of x could actually be L. This x cannot be c. Or we can actually say it this way in words, maybe not quite as precisely, but it says the same thing. If x is within delta of c but is not c, then f of x is within epsilon of L. So there's 3 or 4 different ways of saying this same definition. And depending on your textbook author's preference or your instructor's preference, one or more, they may use a different one of these, but any version of that's still the limit definition. Now, okay, now the next thing I want to do is I want to look at a GeoGebra sketch. So here's a GeoGebra sketch that I've got, and we're going to start with the function 2x minus 3. So any of these things in yellow in this GeoGebra sketch, you can type in. So this types in a formula, 2x minus 3. So y equals 2x minus 3, or f of x equals 2x minus 3, gives us a graph, and it's this graph right here. In this case, of course, that's a line. Slope 2, y-intercept to 0, negative 3. All right, so that gives us the blue graph. Now what we're interested in doing is take the limit of 2x minus 3 as x approaches 2. So we find 2 on the x-axis, and I've drawn a vertical line there with the software. And so we're talking about, now we're not talking about what's on that vertical line. We don't care if the function is defined there or not. In fact, in this case it is. But we're not interested in that. What we're interested in what happens as the blue graph gets closer and closer to that line. Does it approach it as an asymptote, or does it approach two different points on that line, or does it actually approach a single point on that line? And of course we see that the blue graph does approach the orange line at a single point there, which is actually a point on the graph 2, 1. So the limit is 1. Now we put in the value we think the limit is here in this box, cell B8, and that draws a red line here. Now next we establish some value of epsilon. So here I've started with an epsilon equals, let's start with a big epsilon. Let's start with epsilon equals 2. Okay, and so we have this out here. Okay, now what we're looking at is we want the y values to be within epsilon of L. So here's L right here. And if we go to L plus epsilon, that puts you up here. So 1 plus 2 is 3 here. And 1 minus 2 is negative 1. So that's L minus epsilon is here. And so these two green bars here, these two horizontal lines, box out an interval, which is in light green here on the y-axis. And so we want the y values to be within that. Well, here we see the graph, and we see some delta that we could pick, which is controlled by this slider. And notice that if you get all of the y's in here are within that. In fact, the lowest one is actually 0, and the highest one looks like is 2. So they all stay within this part right in here, certainly within that green. Now what if we pick a smaller value of epsilon? So suppose we change that to 1. Now that just squeezed it in further. And actually at delta equals 0.5, it looks like we're exactly where we need to be. If we go in any smaller, then we're just making the y values that are actually used smaller, and they stay within this green band. Okay? What if we go smaller still with epsilon? Let's go to 0.5. So we're making a challenge again. The challenger says, "Oh, I think you're off by 0.5, whatever epsilon is." So what do? We take our claim of the limit, which is 1. We add the 0.5. We subtract the 0.5. That gives us a band here, and we want to show our functions in there. Now, where we are right now, there's a poor choice of delta, because if you look at this, if delta is 0.5, then that makes a band for the x's. It's x plus c plus delta and c minus delta. So c is the thing, the limit. We're taking the limit as x approaches 2. That's where this orange line is. And then this is c plus delta and c minus delta are these two vertical black lines here. Now, if we take these in between here, there are some y's that are outside of my little green strip here. So what we need to do is we need a smaller delta. And so we need to keep bringing this in until what happens? Until all the y values now, if we're within this strip here, if we're between the two black bars, then all the corresponding values on the graph, which are these right in here, are between the two green bars. So if you really look at it, that's the key then is this this little box here, this little purple box. Okay, and so what you want is you want this box to be such that the function, the graph, runs out the right or left sides. It's okay if it goes right at the corner, but it's not okay if it runs out the top or bottom, because, for example, here there's some value here, you know, maybe 2.3 something that's up here, and the y value is further away from L than the epsilon our challenger gave us. But if we go smaller and make it go just at the corner, or even smaller, or anything smaller, then we've shown that we have met that challenge. Now, what is that? What does the challenger do? It says, okay, let's just go even smaller, say 0.1. What do we need to do? we need to make an even smaller delta and keep bringing it in until we're inside there, so that on our rectangle, our little purple rectangle, we're going out the right or left sides. So that's the basic idea here, is that as you squeeze, no matter how much you squeeze in this vertical strip, you can squeeze in the horizontal strip smaller and smaller and smaller, and of course the whole box is then squeezing in on that center of the box, which is where the limit is. Okay, so that's the basic idea of what's going on here. Here's a static picture of the same thing in the notes, but I've already kind of talked about all that. So once again, just in the notes there, kind of go over that. But let's just go over that one more time. So what is this green interval? There's the limit L, which is a y value, and then we have a bar on the top and bottom that's L plus epsilon and L minus epsilon. And so this bar right here gives us the interval. So it gives us the epsilon determines how close we need to be to L. So that determines this vertical interval on the y-axis, and are equivalently where these two horizontal lines are. Of course, the blue is given by the formula, and then what do? We find our x value that we're approaching here, and then we let these, we pick some delta so that we come in here in such a way, we keep making it small enough until we're completely inside here. So what is this interval? This interval goes from c minus delta to c plus delta. And so anything in here except for c itself, we look at that and look at the corresponding y's. So any x in here, you follow it up, you find its y, and you come across, you're going to be inside this green thing, between the two green bars. Okay. Hopefully that helps kind of make some sense of it. So let's look at a couple of example problems and see some things that we might do with this. So suppose we have a function 3x plus 4. Now we know the graph of 3x plus 4 is a solid line. So let's actually go over here and change the function to 3x plus 4. Okay, and there's our solid line over here. And let's keep going back. We want to see what happens as x approaches -1. Now, since it's a solid straight line, that means it's continuous, that limit will be just the function value. So 3 times -1 plus 4, that's 1. So this should be, as x goes closer to -1, y should be closer and closer to 1. So that should be the limit. So let's put that in our sketch over here. We're taking the limit as x approaches -1. So that's the c value. Okay. And the epsilon, we'll get to epsilon in a minute. The limit is actually, what was it again? It was +1. And that's what we've said the limit is. Okay, something looks out of whack here. Let's see, just a minute. 3x plus 4, and we want to go to -1, not -0.1, just -1. There we go. All right, so here's what we have. So here's a question. With the epsilon that I have right now, do we have a small enough delta so that the condition in the definition is true? Well, the answer is no, because how do I know? As I draw this purple box from c minus delta to c plus delta on the side, and L minus epsilon to L plus epsilon here, top to bottom, that purple box, the function graph goes out of the box on the top and bottom sides. It's not small enough. So that particular one, we need a smaller, we need this to get smaller and smaller and smaller. Now we've got a small enough one in there. Okay, let's look back now. Suppose someone now claims that our choice of limit is actually false. Okay? And they claim, okay, we're off by at least 0.1. I've given us an epsilon value. So what we do is go over here. Actually, that's the one I have here, 0.1. Okay? How can we show that their claim is false? That their challenge, how do we defend their challenge? We just have to pick a small enough epsilon in here so that we are, the y values are such that they stay within the y values here as long as our x values stay within this interval here. So as long as x is between c minus delta and c plus delta, then f of x is between L minus epsilon and L plus epsilon. Now, it depends on what my value of delta is, whether I've got the right one. No good there. This in here, this is pretty good. Okay, it's got to be a positive number, can't go all the way to 0. Okay, but we can maybe find the right number in here like that. Okay, so now how do we do this? How would we find the right value? Well, there is a sort of a largest value that would work. See, if we're out here, it's too big. If we come in and it goes, so it's going out of the box on the top and bottom, so that's too big of a delta. If we come in here and it's going out the sides, that's an epsilon that will work. Well, what's the sort of the breaking point, the exact point where it would just sort of just perfectly fit? Well, that's when one, where it does not go out the top or bottom, but it either goes out both the sides, but one of these goes out one of the four corners. So we're interested in where these things cross. Now, in this particular case, so we're talking about where this blue line, the graph, crosses this top green line and or the bottom line. Okay, and those are going to be some of the key values that we're going to be interested in finding. Now, in this case, since it's continuous, and well, since it's increasing, we know that it's going to cross in the upper right corner or the lower left corner. So we want to find where that is. Now, one way we can do that is with a graphing calculator. So we could just graph our function, 3x plus 4, and then our upper and lower things, which are L plus epsilon and L minus epsilon, 1 plus 0.1, or if we want to just type in 1.1, and then L minus epsilon, 1 minus 0.1, or I could just type in 0.9. And those are going to graph, y2 and y3 will graph the two horizontal lines. That's like the two green lines over here on this picture. And then, of course, the 3x plus 4, that's going to graph the function. And then we can just do a calc intersect. Hopefully you know how to do that. And it comes back with an x value here and an x value here. So that's a way we can at least approximately solve that by hand. And in fact, we could probably, right after doing this calc intersect here, if I had gone to the home screen and type x, change to fraction, it would convert that to a fraction as well. Same way for this one here. Now, of course, this is just a linear equation, so it might be just as easy to solve the thing by hand. So what we're doing is we're solving the equation 3x plus 4 equals 1.1. That's going to give us the x value in this top right corner, which should be this right here. So let's see, what do? We subtract 4 first, change this to negative 2.9, then divide by 3. Here it is in repeating decimal form, negative 0.966666. The 6 will repeat forever, or if we do that in a fraction form, that's negative 29 over 30. And similarly, if we want to solve the one where it crosses the other line, that's 3x plus 4 equals the 1 minus 0.1, or 3x plus 4 equals 0.9. So that's f of x equals L minus epsilon, and f of x equals L plus epsilon. And then solve those for x. So here we subtract 4 and then divide by 3, and we see that x is negative 1.03 repeated, 3. The 3 is repeating, or in fraction, which is probably a better way to write it, it's negative 31 over 30. Now, those are the corresponding x values for what? For this box right here. That's the x value of these two vertical lines where it crosses at the corners. What are the corresponding deltas for those? In other words, what's the distance from the orange line to each of these black lines? Okay, so we know that if we take -1 minus -1 minus a -0.96 repeating, and then do that absolute value, that is 0.0333 repeating. Or, in other words, 1/30th. And similarly, if we take -1 minus a -1.03 with the 3 repeating, okay, that gives us 0.03 with the 3 repeating, or 1/30th. Now, in this case, both of those were the same thing. So that means on this picture over here, you're going the same distance either way, you're going to reach a corner. Both corners at the same time. But there are some functions, we may look at one in a later video, where maybe it's not linear, maybe it's quadratic or something, and so to meet where these corners meet, one of these corners is closer to the orange line than the other. If that's the case, you take the smaller of the two distances for your epsilon. So epsilon is the smaller of these two, which is still both the same. I'm sorry, I should have said delta, excuse me, not epsilon. Okay, so this picture here, these are, this distance from the orange to the black is delta. The distance from the red line to the green line is epsilon. Okay, make sure we understand that and don't get it backwards. Okay, so for this epsilon of 0.1, the largest value of delta that would be allowable would be 1/30th, or 0.03 with the 3 repeating. Now, of course, any smaller value would also work. It just wouldn't be the one that would make it go out at the corner. It would make it go out the sides. And so something, for example, 0.03 or 0.01 or 0.001 would still be an acceptable delta. It just wouldn't be the smallest delta. And actually, to get it right where it needs to be, I need to go down to about 0.03. Okay. So let's review. How did I do that? I looked at taking f of x, setting it equal to L plus epsilon, setting f of x equal to L minus epsilon, and solving those two equations to find the two x values for where these things cross. Okay, I can also do this by hand. I can also do it by calc intersect on the calculator. Okay. Then I find the corresponding deltas. Okay, so I could just say, because we know this thing is increasing from left to right, I could have just said -1 plus this value. This value equals 1 plus delta. One of these equals 1 plus delta, and the other one's -1 plus delta. One is -1 minus delta. All right, so with this largest appropriate value of delta, now we can make our window. So we want x going from c plus delta to c minus delta, okay, which is here, same x as we just came up with. And the y's go from L minus epsilon to L plus epsilon, which is here. So then we graph it on that window, and here's our choice of window, x min and x max, y min and y max, just like we had. So the y min is L minus epsilon, the y max is L plus epsilon, the x min is c minus delta, the x max is c plus delta. And what we should see is we should see the graph leaving either one of these right at the corner, and the other one either right at the corner or along the vertical sides, not the top or bottom. Now, how can we formally prove that we've got the right thing? Well, to formally prove this, we need to show that the condition in the definition is true. Okay, so that is, if x is not equal to -1, but it's in the interval from c plus delta to c minus delta, that is in this interval here, or there it is in that. Okay, so x is between there and there. So that's x is, okay, here you can see it on the axis. X is between c minus delta and c plus delta, so these x's, but not at c itself. Okay, so there we are. Then we want to prove that f of x is between L minus epsilon and L plus epsilon, that is between 0.9 and 1.1. So if c is between here and here, here it is in decimal and fractions. So we want x between here and here, but not at -1 itself, which is halfway between these two. So we're going to need to transform. So if we want to transform this inequality, which is this interval here, to this interval here, which is an inequality that'll have f of x in the middle, we have to change x to f of x. So f of x is 3x plus 4. So let's see if we can do that. So we change it first by multiplying by 3. So if you multiply by 3, you have to multiply all three sides by 3. So let's look at the fraction. In the middle, 3 times x is 3x. Then here we distribute the 3. 3 times -1 is -3. 3 times -1/30 is -1/10. And on the right side, 3 times this distributes to give -3 plus 1/10. And then we want to subtract or add 4 to the middle to get 3x plus 4. Okay, when we do that, we add 4 to each of the other parts as well. 4 plus a -3.1 is 0.9. 4 plus a -2.9 is 1.1. And sure enough, that 1.9 and 1.1 are exactly L minus epsilon and L plus epsilon. And we've seen that f of x is in that interval when x, the original x, is in this interval here from c plus delta to c minus delta up to c plus delta. And again, there's an illustration. Now what if, now we go along here, we say, okay, wait a minute, we want to make a smaller epsilon, 0.01, a smaller epsilon. Well, now with the delta that we have, this thing is sticking out the top and bottom, so it's not a good delta anymore. We need to make a smaller delta. Zoom in on the box here. Okay, do we have it small enough yet or not? So just focusing on the rectangle. There's the rectangle. What do you think? Well, we're not small enough. Okay, because this needs to come in such a way that it just meets at the corners, or it leaves out the right or left side, not out the top or bottom. What would it take for it to go right at the corners? Well, it's the same steps we did before. We take f of x and equal to L plus epsilon and solve, again by subtracting 4 and dividing by 3, so that's -299 over 300. Or your decimals, you can see it there. And then we do f of x equals L minus epsilon. That's right here. Okay, and we solve that, and there is x in decimal or fraction form. We could also find at least the decimal form by doing calc intersect, and actually on a calculator they could then change that to fraction and get the exact values there. And so notice these differ from -1 by 1 over 300. So delta is 1 over 300 is the largest value of delta that would be allowable. That generates the window from C plus, that's backwards, from C minus delta to C plus delta, which is what we have here, for x, and x can be anything in that, but x is not c, it's not -1. And when that happens, the f of x is from in the interval from c minus L minus epsilon to L plus epsilon, which is given there. So we could graph this on that window. So we could graph it at 3x plus 4. If you've got the right delta for the given epsilon, you set x min to be c plus c minus epsilon, c minus delta, excuse me, c minus delta, -1 minus the delta we chose. And x max is c plus delta, that's -1 plus the 1/300, I think it was. And it's that. And then the y's then are from L minus epsilon to L plus epsilon, so the y min and y max. That gives us that what you're graphing there corresponds to just the purple rectangle over here in this picture. And on that picture we should see, if we've got the right delta, we should see the graph going out the left and right side, but not the top and bottom. If we have the smallest delta that works, at least one of these two corners will be where the graph goes out of the picture. So if we prove that this is the correct one, let's see, these are backwards again. Fix that. From c minus delta to c plus delta. Okay, and then we want to show that the f of x's are from L minus epsilon to L plus epsilon. So again, this is kind of like before. If we know that x is from -1 minus 1/300, but it's above that, but below -1 plus 1/300, then from that we need to transform the middle part to f of x by first multiplying by 3. To get 3x in the middle. Here it is in fraction, or decimals here. And then add 4, and we get here. But that 3x plus 4 is f of x. And so we've got f of x between 0.99 and 1.01, which is what we want there. Let's see here. I think I did a copy and paste and didn't fix everything yet. So let's see. Delta, epsilon is 0.01. So let's get everything fixed right. That's correct. 0.99 to 1.1. 1.01. Thought one was off a little bit. Yeah, that's correct. Oh, right here. 0.01. 0.01, 0.99, 1.01. There we go. That's the right interval there, which is the one we end up with down here as desired. And there's a static picture of the GeoGebra sketch. Okay, now the next question is, well, can we always do this? Can we always take any value of epsilon that they pick? Can we always find an appropriate delta to bring this in to where we stay within that? So if the x's stay within delta of c, the y's stay within epsilon of L. That's the condition in the definition of the limit. Can we always do this? So the trick now is to say, okay, now let's generalize this. If we take any value of epsilon, how can we take that and come up with the value of delta? Well, what we want to do is kind of look back here at what we've done. So in this first case, we have a epsilon is 0.1, and we ended up with a delta of 1/30th. So epsilon is 1/10, delta was 1/30th. And then when epsilon was 100th, 0.01, 100th, delta was 1/300th. think maybe you can see what would be the relationship between the epsilon and the delta there. How could you write delta as a function of epsilon? That's what we want to do, write delta as a function of epsilon. Well, I think you can see in both cases, it turned out that if we let delta be epsilon over 3, then that's what it works out to be, right? Now notice this is a decreasing function of epsilon, which should always be the case, because as epsilon gets smaller and smaller, delta should be getting smaller and smaller as well. Now let's actually write a formal proof. Okay, so let's actually prove that this is the limit. Now this is how we do a formal proof. So notice we first need to find a formula for delta in terms of epsilon, which is what we've got. Okay, now let's see if we can use that. So here's how the proof goes. Given any value epsilon greater than 0, let delta be epsilon divided by 3. Then if negative 1 minus delta is less than x, which is in turn less than negative 1 plus delta, then by substituting delta equals epsilon over 3, we see that negative 1 minus epsilon over 3, replace the delta by epsilon over 3. You do the same over here. Replace the delta by epsilon over 3. And so this gives us this place of where x is. Now we want to transform the middle into f of x. So multiplying all three sides by 3, we get here. That's going to give us 3x in here. It also is going to give us just an epsilon here and here when we distribute. Also changes this to negative 3 here. Next we add 4 to get 3x plus 4 in the middle. And of course, when we add 4 to here, negative 3 plus 4 is 1. Negative 3 plus 4 is 1 here as well. But that in the middle is f of x. And so what we've shown is, if we take any epsilon greater than 0, if we choose delta equals epsilon over 3, then anytime x is between negative 1 minus delta and negative 1 plus delta, except x may not be negative 1 itself. So let's say x and let's say not equal to negative 1 itself, although in this particular case it doesn't matter. In general, we don't worry about what happens when x equals c. We should have that. And then we've seen that through this series of steps, the f of x is between 1 minus epsilon and 1 plus epsilon. So that says that as x approaches this negative 1 here, that we're within delta of that, then the f of x, the 3x minus 4, is close to 1 within epsilon of the 1. And no matter how small, given any epsilon greater than 0, we can choose the delta so that this stuff works out, and that is what makes that the definition. So I think we'll stop this video here, and we'll come back and do another example or two in the next couple of videos.